So our next video in the data science series is dimension reduction. In this video, we will learn about what is dimension reduction, tackling multicollinearity, and leverage PCA. In this video, we dive into the world of dimension reduction, exploring how to tackle the challenges posed by multicollinearity in your data. We will discover the power of principal component analysis (PCA) and its application in data analysis. Join us as we uncover insights and empower you to simplify complex datasets. So let us understand what is multicollinearity. The problem. Multicollinearity occurs when independent variables in a dataset are highly correlated, creating redundancy and hindering model accuracy. This makes it difficult to isolate the individual effects of each variable, leading to unstable coefficient estimates. Then the consequences. High multicollinearity can result in inflated standard errors, unreliable p-values, and unstable model coefficients. It also makes it challenging to interpret the relationship between variables, leading to inaccurate conclusions. Let us now understand how we detect multicollinearity in R and Python. Correlation matrix. Visualizing the correlation matrix reveals the relationship between variables. Looks for high absolute correlations, example above zero point 0.8, to identify potential multicollinearity. Variance inflation variance inflation factor. VIF measures how much the variance of a coefficient is inflated due to multicollinearity. Values greater than 5 or 10 indicate significant multicollinearity. Then third is eigenvalues and condition numbers. Eigenvalues and condition number from the correlation matrix can also be used to assess multicollinearity. Low eigenvalues or high condition numbers signal multicollinearity. What is principal component analysis, or also short form PCA? PCA is a powerful dimension reduction technique that transforms correlated variables into a set of uncorrelated principal components. These components capture the maximum variance in the data, allowing you to represent data in fewer dimensions while retaining the most of the information. Preparing data for PCA in Python. First is scaling. Scaling data ensures that all variables have similar ranges, preventing variables with larger scales from dominating the analysis. Normalization. Normalization transforms data to a specific range, example 0 to 1, equalizing the influence of variable with different scales and units. Then third is feature selection. Select relevant variables for PCA. Remove highly correlated variables or features with low variance as they might not contribute significantly to the analysis. So now we understand how we can perform PCA in Python. So first of all, import libraries. Import necessary libraries like SCI kit, learn for PCA implementation, and pandas for data manipulation. Then second, create PCA object. Instantiate a PCA object specifying the desired number of components or the explained variance ratio. Then third, fit the PCA. Train the PCA model on the prepared data, allowing it to learn the principal components from the data. Then fourth is transform the data. Apply the learned PCA transformation to the data to project it onto the lower dimensional space. So now we understand how we can interpret the PCA results. The first way is eigenvalues. Eigenvalues represent the variance explained by each principal component, indicating their importance. Then second is loadings. Loadings show the correlation between each original value and the principal components, providing insights into how the original variables contribute to the components. Then third is scores. Scores are the transformed data points in the lower dimensional space, representing each data point in terms of the principal components. Selecting optimal number of principal components. First, scree plot. The scree plot visualizes the eigenvalues against the number of components. The elbow point where the eigenvalues start to flatten suggests the optimal number of components. Then second is explained variance ratio. Assess the Cumulative explained variance ratio. Choose the number of components that capture a sufficiently high percentage of the total variance. Example 80 to 90%. Then third is domain knowledge. Consider domain expertise when selecting the optimal number of components. Prior knowledge can help determine a suitable balance between dimensionality, reduction, and information retention. So now we understand some of the applications and limitations of PCA. Data visualization. PCA helps visualize high-dimensional data in lower dimensional dimensions, enabling insights into relationships and patterns. Feature extraction. PCA extracts relevant features from data, reducing the dimensionality of the data while retaining important information. Model improvement. PCA can improve model performance by reducing multicollinearity and enhancing model interpretability. Data compression. PCA can compress data, reducing storage space and computational cost while preserving key information. So these are some of the applications and limitations of PCA. So this is all for the video. Thank you.